Welcome and thank you very much for joining today our web seminar on plasma dicing APX300 from Panasonic Industry Europe. I'm James Weber and we are live from the Panasonic campus in Munich. Just like to give you a quick overview. It's our brand new customer experience center built with over 6,000 square meters purposely for our customers and with our permanent demonstration centers, labs, a customer experience center. Today I'm going to be giving you a web seminar on our APX300 plasma dicer system. I'd like to take around 30 minutes of your time. We're going to, first up, we're going to show you a video about the brand new customer experience center. Then I'm going to show you a presentation on our plasma dicer technology and the applications. Then we'll move over to a video from our demo center in Japan, in Osaka. We'll show you more details about the machine, how it works, and how it's operated. Then we'd like to open it up to Q&A. My colleagues in Japan are online to support, to take your questions. So please feel free, as I'm talking throughout the whole web seminar today, to put your questions in the chat. And then we'll do our best to answer those as quickly as possible. I guess my plan, I'll collect the questions and then we can go through them verbally. So first up, I'd like to show you a video on the brand new Customer Experience Center, give you an impression of our features for our customers. So let's take a look now.
The Panasonic Campus Munich will foster collaboration and synergies across different Panasonic companies, including industry, life solutions, appliances, and connected solutions.
It's a combined work and experience place where people are working day on day in their offices, the meeting rooms, the laboratories, the tech centers, combined with a very attractive customer experience center.
Now, for the first time, Factory Solutions is able to present all product lines in one location here at the campus in Munich.
The new campus offers us the opportunity to invite our customers and express our vision in systems and solutions to be a reliable partner in their projects.
The new campus is a sophisticated showroom area.
This great brand exhibition will enhance our brand awareness and visibility in Europe.
The Panasonic Campus Munich will enhance sales and position Panasonic Industry Europe as an industry leader and solution provider.
I hope that gave you a good impression of our brand new Panasonic campus in Munich. As I mentioned, it's for our customers and we are very much looking forward to inviting you here as soon as we can. Even behind me is our brand new purpose-built Microelectronics demo and application center with our full lineup of other equipment, microelectronics equipment, so our flip chip bonder and plasma cleaner, along with a full suite of analysis equipment. So we are very much looking forward to invite you here as soon as possible. So now I'd like to move into the presentation on the APX300. I'll give you an overview of the benefits and applications of the APX300. So first up, the general features of plasma dicing. Of course, everyone knows blade dicing, how to separate the wafer, but as you can see on the left, this is a mechanical process. It's often leading to chipping. Whereas the new technology application of dicing a wafer can be plasma dicing, gas etching of the whole wafer. So a mask is put on top of the wafer and instead of a line-by-line dicing action, it's a chemical etching of the wafer and the whole wafer is etched in one go. So this is a general trend of the market, it's getting more and more like this. It's been like this, of course, for years, but everything is getting brittle, thinner and smaller. You can even see on the right-hand side, this is a finger. It gives you an idea of the kind of devices that we are dicing these days. So with these trends, the following issues happen. Of course, chipping, as I mentioned, from the mechanical action of the blade dicing. As the devices get smaller, more and more cuts or lines need to be cut on the wafer. So process time increases. And as the devices get smaller, the blade width stays large relative to the actual device. So there is potentially loss of yield. So plasma dicing can address these problems, but first up, it's important to notice that it's firstly an economics decision. It cannot replace all applications, but as we move into this area in the blue section of smaller chip size and thinner wafers, plasma dicing definitely returns its investment very quickly for customers who decide to invest. With that being said, though, thicker wafers are also possible to be diced if your objectives are more in the terms of quality. So if we look at the benefits of plasma dicing lined up against blade dicing, for small chips, we can see with the blade dicing width, a dicing street width of 60 micrometers, we can go down to even 5 micrometers with plasma dicing, increasing yield. Process time can be much shorter because, as I said, the dicing is performed on the whole wafer at once. So instead of it being based on line-by-line time, it's more based on the thickness and the composition of the wafer. It's a totally particle-free process, so especially for image sensors and devices that need particle-free end result, this is a perfect technology. And for memory, for example, like memory devices and other chips or wafers that are brittle, plasma dicing is very appropriate because it's a damage-free process. So the general principle of plasma dicing, it's a cyclic etching process. As you can see here, the wafer is mounted on dicing frame with tape, inserted into the plasma chamber, and then you have a process known as the Bosch process consisting of deposition, breakthrough, main etching, and then this repeats, as you can see in the yellow arrow, until the wafer is entirely diced. You can see here evidence of the damage caused by blade dicing on the left, and on the right-hand side you see plasma dicing result completely damage-free. Here's a closer look. If you look underneath or on the side of blade diced chips, you can see evidence of damage. And on the right-hand side you can see evidence of plasma diced chips, totally damage-free result. Because of the damage-free, this leads to much stronger chip strength. If we subject these chips to a 3-point bending test, as you can see here, with blade dicing on the left and plasma dicing on the right, you can see that the plasma dicing chips are much stronger. Why is that? Well, if you subject these chips to a 3-point bending test, the cracks propagate through the damage that's caused on the edge of the chip. Whereas if you do this with plasma dicing, it's actually approaching the strength of a natural silicon, so it tends to crush. You can see here an example of how yield can be increased. Kerf width has been reduced to 5 micrometers with plasma dicing. So if we take an example of a 12-inch wafer with a 0.4 millimeter by 0.4 millimeter device, and we reduce from 60 micrometers to 5 micrometers, you can increase the yield by 33%. So you can imagine the gains in production that can be achieved just by this process, which definitely plays a big role in the return on investment calculation. Also, another benefit of plasma dicing is the flexibility you have in chip shape, design, and layout on the wafer. So if you have large chips or oddly shaped chips that aren't totally square or that don't fit into a grid alignment. You can do anything you want with plasma dicing. It basically depends on the mask layout. So if going into more detail, the APX300 plasma dicer from Panasonic, this is our machine, you can see on the right, in a single chamber configuration. It consists of a main unit and a transfer unit at the front. But also possible to upgrade our system into a multi-chamber system. You can see here in a 1, 2, or 3 chamber configuration. The main unit is the same, but the front load lock system is replaced with a wafer transfer module and the EF-EM. So as I said, from 1 to up to 3 chambers. So some space savings there, and definitely optimal for a mass production scenario. So if we line up the single versus the multi-chamber configuration, you can see the different application scenarios. So in terms of production, single chamber system gives you very high flexibility, so good for R&D, high product mix, and then from low to high volume. So it can give you a good chance to, let's say, get your feet in the water and ramp up. It's also possible, as you can see, to exchange the front and replace it with more advanced wafer handling system. So the main investment, of course, is the main unit, and this is common throughout the configurations. So the cassette for the single system is a 13-slot cassette, and it's loaded one at a time. We'll show you this in the video coming up. And again, with the multi-chamber configuration, much more high-volume scenario with up to 4 cassettes being loaded. Both are handling 200 and 300 millimeter dicing frames. And of course, the multi-chamber configuration is handling all of this with multiple cassettes. And the single chamber system is also handling this fully automatically. We take a closer look inside the machine. Also, we'll talk about this in the video coming up, but just give you a quick overview here. So the main unit is consisting of the process chamber, RF generator, and power supply, etc. So enhanced ICP plasma source, inbuilt endpoint monitoring through optical emission spectroscopy. We are able to use fluorine-based gases, chlorine-based gases, and other kinds, of course, to achieve your etching requirements. Fluorine-based is most popular for silicon applications. Inbuilt waferless dry cleaning function inside the machine to enable easy maintenance. Yes, as you can see here, cross-section of the plasma dicer ESC electrode and dicing ring cover, which I'll go into a little bit of detail here. So the wafers are mounted on tape and frame, and if we just put those in to be etched, the tape is susceptible to melting due to the high heat generated during plasma dicing. So we've had to design features to control that. So we do that through the Panasonic designed electrostatic chuck and cover ring. So as you can see on the right, electrostatic chuck providing good cooling and strong attachment force between the wafer, tape, and the chuck. And the cover ring, which is designed for the size of the wafer, which is lowered after the wafer is entered into the chamber to protect from the wafer edge all the way to the edge of the frame. So very important for us to maintain wafer temperature and tape temperature during dicing so that maximum etch rate can be achieved. So wafer remaining at 50 degrees Celsius, tape remaining less than 50 degrees Celsius, and frame less than 43 degrees Celsius through our own independent experiment. So looking at the performance of the APX300, taking the Bosch process silicon dicing example, we can achieve up to 35 micrometers per minute dicing speed. Uniformity is a high priority for us, so on the wafer it's less than 3%, and wafer to wafer we also maintain less than 3%. It's possible for us to suppress notching. So this is very important for almost all of our customers. As soon as we get to the end of the wafer, the bottom of the wafer through dicing, make sure that we don't over-etch or create notching. Ashing to remove the photoresist, it's all integrated in the same chamber, so no need to remove the wafers or purchase additional equipment. It's possible for us to dice multi-layer wafers, all in the same chamber. You can see on the bottom right examples of, well, the first one is an example of a relatively high aspect ratio, so 5 micrometer opening and 150 micrometer etching depth, very small scallops, 0.5 micrometer, and an etching rate of 18 micrometers per minute. Whereas, as I said, we can go all the way up to 725 micrometers with slightly larger scallops, 1.5 micrometers, and still provide a, in this case, it was a 100 micrometer street width, so relatively fast dicing speed of 33 micrometers per minute. And then in the left side, bottom left, we can give you a good idea of etching speed of different layers. So, for example, silicon dioxide, silicon nitride, gallium arsenide, which is becoming much more popular with VIC cells, for example, and even organic layers, die-attach film and polyimide. So I'll show you a few scenarios, 4 different scenarios of plasma dicing process flows. So on the top layer in blue, you can see basically the scenario for wafers that have some metal in the dicing street. This needs to be removed with laser. We can achieve this with 2 different process scenarios, and then the other one underneath I will show is with a photolithography approach. So first up, one of the laser patterning and laser grooving scenarios. So we offer BG tape mask with laser grooving and plasma dicing. That's those letters at the top. So first we backgrind the wafer. Then a special tape we can offer through one of our partner companies, Furukawa. We remove or delaminate the backgrinding tape with leaving this yellow mask layer underneath. This mask layer is then patterned with the laser, and then where there's no, basically where the pattern has been removed or where the mask has been removed by the laser, plasma will etch. So this has benefits. It's easy to use, and part of the backgrounding tape is utilized as a mask, so no other protection layer is needed. And there's, of course, a shorter process time. The alternative to that is to use a water-solvable mask. So that's WSM plus LG laser grooving plus plasma dicing. So the water-soluble mask is applied by spin or spray coating. The laser patterning then patterns the mask. We then put this inside the chamber, perform plasma dicing, and then after the dicing, the water-soluble mask is basically washed off. You can see a typical example of a wafer structure on the bottom left. So in this case, there's some metal in the dicing street that first needs to be removed. So the laser patterning is used to pattern the wafer and at the same time remove metal. And as you can see, it's also no problem to handle wafers with bumps or pads. For this application, it's a very helpful feature that we've built into our machine using Panasonic patented technology. So the wafer is first patterned, and you can see on the bottom left picture quite some, let's say, jagged mask edge there. So if you perform the plasma cleaning inside the plasma chamber, it can clean things up quite a lot before we start to dice. Then by far the most popular option, at least in Europe, is the photolithography approach. So similarly, the wafer is coated with photoresist. Then it's exposed and developed So the mask is removed in the sections that you wish to dice. Then the wafer is inserted into the plasma chamber, dicing is performed, and then inside the chamber we can perform ashing to remove the remaining mask, and then after that you have the fully singulated wafer mounted on dicing tape and frame. So you can see again in the bottom left an example of a wafer structure. So also no problem to handle bump and pad, and maybe even silicon nitride layer. With the help of our partners, so in this case thanks to EVG, spray coating of relatively large bumps is also easy for us to achieve. Definitely in Europe this is becoming more and more popular, almost all applications like this. So in summary, if you're a customer and you're listening to this presentation, and you should think to yourself, why should I consider plasma dicing, or why should I think about upgrading? Well, the first is better quality. It's a totally particle-free process, and as I said, no mechanical damage, which leads to higher chip strength. And if you have very high fidelity, for example, sensor chips that are very expensive, maybe you can have huge gains by providing a much better quality to your product, quality product to your customers with much cleaner and damage-free sidewalls. If your devices are small, you can definitely increase your yield. This is without question, going down, as I mentioned, to 5 micrometers dicing street width. Speed can be greatly increased, so this definitely also helps with your return on investment. The wafer is diced in one hit, so now it depends on the thickness of the wafer. So if we can achieve thinner wafer thickness, speed can be increased. Flexibility is also very high with plasma dicing, so you can decide layout of the wafer, and as I said, if you have large sensors which are not square, these are possible to imagine. And yes, all of these things put together basically lead to cost savings and a very good ROI. So, welcome back, and thank you for listening. As I said, if you have any questions, please feel free to write them in the chat, and my colleagues will look at them and collect them, and then we can go through them at the end. So I talked about the features and possible applications of plasma dicing. So now we'd like to show you how that all works. So we've got a fully functional demo center in Osaka, in Japan. And my colleagues have very kindly prepared a video for us to show you an introduction of the demo center. And we'd like to show you that now. Let's take a look.
Welcome to Panasonic Smart Factory Solutions. It's my pleasure to introduce you to the Panasonic Plasma Dicing Demonstration Center, or PDDC, in Osaka, Japan. The PDDC is a fully operational demonstration center run under clean room conditions, where Panasonic promotes its APX300 plasma dicer lineup in both 8-inch and 12-inch configurations. In addition, we have an array of equipment necessary to prepare our customers' samples, such as back grinding, photolithography, and laser patterning, as well as frame mounting and demounting equipments, and a complete lineup of analysis equipment such as SEM and optical microscopies. I'm Shogo Okita, and today I will guide you through an overview of our APX300 plasma dicer and PDDC. Here you see the APX300 plasma dicer, and now I would like to explain some of its features. The APX300 plasma dicer is available in either an 8-inch or 12-inch configuration. In order to perform plasma dicing in the APX300, all wafers must be mounted on dicing ring frames The 8-inch or 12-inch specification refers to the ring frame size, which are the standards in the semiconductor industry. Conventional dicing tape are also able to be used. All APX300 plasma dicer models feature an enhanced ICP plasma source. Plasma is generated by a patented Panasonic design multi-spiral coil with the shower gas head induced uniform gas flow into the process chamber. The plasma source is low inductance and high efficiency, and this produces a very high density and uniform large-scale plasma over a wide range of discharge. The main objection of this design is uniform dicing from the center to the outer edge of the wafer. The APX300 is most commonly utilized to dice silicon wafers by cyclic etching, but the APX300 has numerous other capabilities such as cyclic etching of newer materials such as gallium arsenide, as well as isotropic etching, etching of cavities or beads, etching of oxide layers, stacked wafer, or even organic layers. The APX300 is easy to operate. It's all controlled by an integrated touchscreen monitor. There are indeed two monitors, one at the front and one at the back of the machine for easy access, but only one of the monitors can be used at a time to ensure total control of the operator. Parameters such as the dicing recipe, quantity of wafers in the cassette are entered by touch, and as you can see, a recipe can easily be loaded from the APX300's database. The APX300's wafer cassette has 13 slots and is easily loaded into the load lock chamber at atmospheric pressure by an operator at the front of the machine. The operator simply fills the cassette, opens the load lock doors, loads the cassette, and closes the load lock door. Commencing production is also very easy. Once the cassette is loaded into the load lock, the APX300 can be introduced to start. The load lock pressure is lowered, and the inbuilt handling robot takes out each of the 13 wafers one at a time and loads them into the process chamber for dicing. One cassette's worth of wafers can be consecutively etched fully automatically. Panasonic's intention is to demonstrate the APX300's capability to our customers. This is why we established the PDDC in 2016. It's over 230 square meters and it's located just 20 minutes outside of downtown Osaka. We will highlighted previously, the PDDC features both our 8-inch and 12-inch APX300 plasma dicer models, and it is operated under Class 1000 clean room conditions. In addition to our APX300 plasma dicers, we also offer our customers the service of backgrinding, laser patterning, and full suite of photolithography equipment. Panasonic offers everything our customers need, so that when you send us your wafers, that's it, we handled everything. Not only that, after we have diced the wafers, we can analyze the samples in the very same room. We offer a state-of-the-art scanning electron microscopy and a full suite of optical and laser microscopies. Usually, Panasonic performs several demonstrations until a dicing recipe is fully developed. This recipe is developed through close collaboration between the PDDC's process engineers, Panasonic Industry Europe's local sales representatives, and of course our customers' production and R&D engineers. Finally, we want to strongly stress that Panasonic can only achieve its great result with the excellent support we received from our collaboration partners, starting from the material suppliers, backgrinding suppliers, photolithography vendors, all the way to our measurement equipment suppliers. We would especially like to thank Acratech and EBG for their close and never-ending support. Panasonic works hard to ensure this equipment chain is easily structured for our customers with the aim of seamless integration plasma dicing into existing production environments. We call this the total solutions approach. With that, I would like to thank you for your attention, and I hope you received a good overview of the PDDC and the APX300 plasma dicer. If you have any questions, feel free to ask us anytime. We are here for customers. Please contact Panasonic Industry Europe to organize a demonstration. We very much hope to welcome you to Osaka very soon. 大変ありがとうございました。
So welcome back, and I hope that video gave you a very good impression of our capabilities in Osaka. So two important points I'd like to just highlight again. Just like our brand new campus Munich, Panasonic campus Munich, and a customer experience center, we've designed the plasma dicing demo center for our customers. So please make use of it. We are here for you. So through me in Europe and my colleagues in Asia, we can definitely collect your requirements and find a solution for you. And then our intention is to make sure that we demonstrate that we can achieve what we promise. So I hope we gave you a good impression that if you send us the wafers, basically we perform everything, give you a full report and send it back, and then you be the judge. Second point is the total solutions approach. We really mean that. We know that plasma dicing is a new technology and it needs to be integrated into the existing framework, which is expensive and difficult. So we are also flexible with that, and that's why it's essential that we have a good relationship with suppliers from the beginning all the way to the end, so our collaboration partners. So we think that's our biggest advantage against our competitors. So during the chat, during the video, I definitely received a lot of chat messages. You can see I'm on the tablet here. Tried to go through it live. So we're coming up on 40 minutes, so I tried to just spend 5 minutes or so going through these questions. If I don't answer your question, you can see on the screen, please get in touch with me personally, and I'll definitely follow it up with you personally and with our process engineers in Japan. So one of the questions which popped up a lot was, can we dice DAF, as a die attach film? I think we showed that in the video, one example, and I can definitely show you that in more detail by email. We can dice organic layers. Another popular question was the etching of silicon carbide. Unfortunately, I wish we could, but physics is in the way. It's just too difficult to dice through it. So in general, this is not an application that we can promote. One good question was the contamination of the chamber if you switch from dicing different materials, so silicon and then, for example, gallium arsenide. This is a concern that you need to keep in mind. So if you do have an R&D picture in mind, you'd have to factor in complicated decontamination operations. So if you switch from silicon and then gallium arsenide, you'll need to clean the chamber completely before going back to silicon. So in cases where we have customers dicing both of those or different types of products, we recommend more than one machine to minimize the downtime caused by chamber decontamination. It's a good question. So yeah, we need to think about this right from the beginning, how the whole process fits together. There was another question about the coverage of the tape. So in my presentation, I mentioned this Panasonic design cover ring. So we provide you with a cover ring which is tailored to the wafer size. And this takes only 5 to 10 minutes. Open the chamber, pull the two halves out, and put it in and close the chamber. So 5 minutes change and 10 minutes to close everything up, which is then suitable for the wafer we are etching. It comes down after the wafer is in the chamber and protects the edge of the wafer all the way to the edge of the frame, so the tape and the frame don't see plasma dicing during etching. One of our machine's greatest features. One question I get a lot from customers is the maintenance time. So we recommend based on activation of RF time, so between 300 and 500 hours, we recommend full chamber maintenance, full chamber cleaning. So this takes generally a whole shift to complete. So it's something that needs to be factored in to production. But with that being said, our machine does offer an inbuilt dry cleaning function. So maybe you can program it as you wish after every cassette. So after 13 wafers are etched, the machine can perform a dry etching step. So basically, without any wafers loaded, the machine can generate plasma inside the chamber and clean itself. It's another feature of our machine. There's many questions coming in. I'll follow up on these after the web seminar. I don't want to take up too much of your time going through every single one. And thank you very much for writing these questions. Yes, as we mentioned before, please get in touch with us by email. It'll be on the screen again in a second. Almost all commercially available dicing tapes are able to be used, so don't worry about that. Again, we have close collaboration with all the major vendors, so we can definitely find a solution for you there and integrate it into your existing production lineup. Yeah, I think I'll finish it up there. We're approaching 45 minutes. So don't worry, I'll follow up with you personally after this web seminar. I'd like to thank you very much for joining. Thank you very much for your interaction. We are very much looking forward to meeting you here in Munich, or even taking you to Osaka, hopefully this year, once things get back to normal. We'd like to thank you for joining, and we look forward to welcoming you for the next web seminar this year at some time. Thank you very much.